and welcome to Business Calculus First Derivative Test Applications. Throughout algebra and calculus, we have looked at the graphs of many functions. Typically, we interpret these graphs as a series of input values on the horizontal axis and the corresponding output values on the vertical axis. However, we may plot the rate of change as a function on the vertical axis and think of this as the first derivative of another function. This allows us to imagine the graph of the function and analyze it by looking at the graph of the derivative. So, today's video is going to be a visual exercise where we learn how to interpret the graphs of these first derivatives of functions. Let's look at the following example involving price analysis. This graph of b prime of t approximates the rate of change of bacon over 70 months, where b of t is the price of sliced bacon in dollars and t is the time in months. What we would like to do is write a description of the graph of y equals b of t, the function that the pictured function is a derivative of, including a description of local extrema of the graph of y equals b of t. And we would like to sketch a plausible graph for b of t itself. Here we have the same graph, b prime of t, and we would like to put it in a context where it's a little bit easier to work with. So we can draw it. Okay, part A asks us to look at the possible local extrema of a graph y equals b of t. Now, the local extrema are going to occur where the derivative of a function is equal to 0, potentially. We see that in these regions, the function is negative, and in this region, the function is positive. So, in the red regions, the function is going to be decreasing, and it's going to be increasing in the green region. So let's make a note of that. We are decreasing from 0 to, let's say, 12, and also from 58 to 70. The function is going to be increasing in the region in the middle, so from 12 to 58 months. If we have a local minimum for our function, it's going to occur when x equals 12. And if we have a local max, it's going to occur when the function is equal to 58. Again, because we are decreasing in this region, increasing in this region, and decreasing in this region. Now what we're going to do is draw a potential sketch of the graph. We don't have any information about the actual values, so we're just going to do our best to sketch something that's reasonable. So this is going to be a graph of b of t. And we're going to have the t-axis down here match the axis of the function directly above it. So if I have some sort of local min, it's going to occur at about 12. And if I have some sort of local max, it's going to occur about 58. And so we have a function that decreases up to this point, increases up to this point, and then decreases for the rest of its domain. Okay? And again, we're just following the patterns based on the fact that this is a graph of the first derivative. So here's our sketch. For our second example, we're going to look at revenue analysis. And this time we're going to have a graph of the total revenue, r of x, and we're going to speculate what the derivative of this function looks like. Our total revenue r of x from the sale of x cabinets is given by the pictured graph, and what we would like to do is write a description of the marginal revenue function, r prime, including any possible x-intercepts of that graph. And then we would like to sketch a possibility for the graph of y equals r of x. All right, we have our function r of x, and we would like to determine the properties of the derivative of this graph. We see right away that there is a local max at this point here, and we're going to signify the fact that there is a horizontal tangent line there with that line. So at approximately x equals 500, we're going to have an x-intercept for our graph of r of x, r prime of x, excuse me. As for the rest of the graph, we see that in this region, the function is increasing, and in this region, the function is decreasing. Over here, r prime is going to be positive, and over here, r prime is going to be negative. Okay, now we have enough information to draw our graph for r prime. So we're going to be graphing r prime of x. We're going to use the same axes as our previous graph, especially in the x direction. We'll mark off 1 to 1,000 here. And we see that at approximately x equals 500, we know we're going to have our x-intercept, because that's when the function switches from being positive to being negative. And we have some value up here, and our function is just going to decrease and remain positive until it hits our intercept, and then it is going to become negative and decrease down to x equals 1,000. Most important features here are the fact that the function is positive in this region and negative in this region, and it intercepts the graph where our horizontal tangent line occurs. The graph on the left is the derivative of a function f. So we have the graph of y equals f prime, and I would like for you to determine which of the graphs on the right could potentially be y equals f of x. Thank you very much for listening. I'll see you next time.